Hello, dear students, friends. Today we will take some numerical problems on unsteady flow. First one, a circular tank of diameter 3 meter contains water up to a height of 4 meter. The tank is provided with an orifice of diameter 0.4 meter at the bottom. Find the time taken by water to fall from 4 meter to 2 meter, one case. In the second case, if it is required to be completely emptying the tank, take coefficient of discharge of orifice 0.6. Solution, you can see here, dia of the tank given 3 meter, area A is equal to pi divided by 4 multiplied by 3 squared, that is 7.068 meter squared. Dia of orifice small d is equal to 0.4 meter, therefore area of orifice is equal to 0.1257 meter squared. Initial height of water h1 is equal to 4 meter. Final height of water case 1 h2 is equal to 2 meter and h2 is equal to 0. Now case 1, when h2 is equal to 2 meter, we know that the formula T is equal to 2a whole multiplied by under the root h1 minus root h2 divided by CDA root 2g. Substitute all the values, you will get time required to empty the tank from 4 meter to 2 meter is equal to 24.8 seconds. Case 2, when we are required to completely empty the tank, the formula is given here. We have to substitute just h1 value, h2 value is equal to 0. Therefore, we will get the time required is equal to 84.6 seconds. So, this you can observe from the previous case, it was hardly 24.8 seconds. Now, in this case, it is 84.6 seconds. Next problem. A hemispherical tank means in the previous problem, area was constant, circular. Now, area is different, variable. A hemispherical tank of 2 meter radius is provided with an orifice of 40 millimeter at its bottom. It contains water up to a height of 1.8 meter. Find the time required by water to fall from 1.8 meter to 1.2 meter, first case. In the second case, we have to completely empty the tank, means h2 should be equal to 0. Take coefficient of discharge of orifice or opening as 0.62. Now, solution. Radius of the tank r is equal to 2 meter, given d is equal to 0.04 meter. Therefore, area is equal to 1.2566 into 10 to the power of minus 3 meter squared. Initial height of water 1.8 meter. Coefficient of discharge is equal to 0.62. Now, the time required by water to fall from 1.8 meters to 1.2 meter, case first. h1 is equal to 1.8, h2 is equal to 1.2. As usual, we know the formula for this as T is equal to pi divided by CDA root 2g whole multiplied by 4 by 3 r whole multiplied by h1 to the power of 3 by 2 minus h2 to the power of 3 by 2 minus 2 by 5 whole multiplied by h1 to the power of 5 by 2 minus h2 to the power of 5 by 2. If you substitute the values, you will get T is equal to 27 minutes 43 seconds or 1663 seconds. Next case, when it is to be completely empty, then we have to put h2 is equal to 0, whereas h1 is equal to 1.8 meter. For that, formula is given by T is equal to pi by CDA root 2g whole multiplied by 4 by 3 or h1 to the power of 3 by 2 minus 2 by 5 h1 to the power of 5 by 2. If you substitute the value, you will get the total time required is 4280.5 seconds or 71 minutes 20.5 seconds. Next problem. Third problem. In a pipe, it is on water hammer. In a pipe 600 millimeter diameter and 3000 meter length, provided with a valve at its end. Water is flowing with a velocity of 2 meters per second. Assuming velocity of pressure wave C, capital C, is equal to 1500 meters per second, find the rise in pressure if the valve is closed in 20 seconds. First case. Second case, if the valve is closed in 2.5 seconds. In 2.5 seconds. Assume the pipe is to be rigid one and take bulk modulus of water as 2 giganewton per meter squared, that is equal to 2 into 10 to the power of 9 Newton per meter squared. Solution. All the data you have to write in the form of symbol. Dia of pipe D is equal to 0.6 meter. Length of pipe L is equal to 3000 meter, sorry, wrongly printed. V is equal to 2 meters per second. C is equal to 1500 meters per second. Now, case 1, rise in pressure P. Time taken to close the valve T is equal to now 20 seconds. Let us find out the critical time 2L by C, that works out to be equal to 4 seconds. 4 seconds. 4 seconds. Means T is given time is greater than 2L by C because it is given as 20 seconds. Therefore, the valve closure is gradual. Hence, it is closed gradually. Therefore, we have pressure rise is equal to rho LV by T. If you substitute, you will get 300 kilonewton per meter squared. Next case. When time taken to close the valve T is equal to 2.5 seconds. Bulk modulus of water K is equal to 2 giganewton per meter squared. Velocity of pressure wave is given by C is equal to under the root K by P, where K is 2 into 10 to the power of 9 divided by rho is mass density of fluid 1000 kg per meter cube. Therefore, this is about 1415 meters per second. Now the ratio 2L by C is equal to 4.24 seconds. That means given time T 2.5 seconds is less than 4.24. Hence, the valve is closed instantaneously. Got the point? Therefore, rise in pressure P, when the pipe is rigid, the rise in pressure due to instantaneous closure of the valve is given by P is equal to rho VC, where V is equal to 2, rho is 1000, and C we have calculated 1414.2 Newton per meter squared. Therefore, the total net answer is 2828.4 kilonewton per meter squared. This will be equal to 2828.4 kilonewton per meter squared. That's all, very simple. Only thing is you have to substitute very carefully with conversion of units. Sometimes instead of pipe length 3000 meter, they may give you 3 kilometer. Then straight away 3 kilometer should not be substituted, it should be converted into meter. That's all. If it is in millimeter, you have to convert into meter. Even if it is in centimeter, you have to convert that into meter. All units should be single. Next problem. Last problem. When the pipe is considered to be an elastic. Water is flowing in a pipe of 150 mm diameter with a velocity of 2.5 meters per second when it is suddenly brought to rest by closing the valve. Suddenly. Find the pressure rise assuming pipe is elastic, of which Young's modulus E is equal to 2.06 giganewton per meter squared. Poissonous ratio 0.25, that is 1 upon m is equal to 0.25, and K for water, that is Bulk modulus of elasticity of water is given as 2.06 giganewton per meter squared. Pipe wall thickness, that is small t, is given as 5 mm. 5 mm. Now we will see the solution. Diameter of the pipe D is equal to so and so 0.15 meter. Thickness 0.005 meter because it is 5 mm. Velocity of water 2.5 meters per second. Modulus of elasticity given. Bulk modulus of elasticity of water is given. Poisson's ratio, as I have already told, 1 upon m is equal to 1 upon 4, that is equal to 0.25. Solution. Pressure rise P using the relation P is equal to V under the root P divided by 1 upon K plus D by ET, where T is the thickness, E is the Young's modulus of material, K is the bulk modulus of water, and D is the diameter of the pipe, P is the pressure, V is the velocity. If you substitute, this is rho. This is rho is equal to density 1000 kg per meter cube. 1000 kg per meter cube. If you substitute all the values, you will get 3148 kilonewton per meter squared. So in order to conclude this unit 1b along with practical examples, numerical problems, I would like to appeal to all students that take the data from the question paper very correctly, with patience, then convert all different units into single unit and then substitute correctly. Also, you write the answer with the unit. Otherwise, without your knowledge, you may be losing overall in this subject around 8 to 10 marks just if you do not write the units. Please keep in mind to write unit for answers. Okay? Thank you. We will continue in the next class. Thank you.